South of Aswan, where the Nile narrows against pink granite bedrock, a length of stone the size of a small building still lies exactly where it was abandoned 3,500 years ago. It is called the Unfinished Obelisk, and it never left the ground. Somewhere in the final stages of quarrying, a crack split through the rock, and the entire project stopped mid-motion. What it left behind is not a monument. It is a record of the exact moment ancient Egyptian granite work was interrupted, still carrying the marks of the tools that made it. Along one edge, dozens of shallow, rounded grooves run in a tight, even row. The trench workers cut to free the stone from the bedrock beneath it. In a case at a museum in London sit 6 short cylinders of that same hard pink stone, each one bored clean through with a narrow, perfectly centered hole. A Victorian archaeologist pulled them out of the sand at Giza more than a century ago, and nobody has ever fully agreed on how they were made. Granite is not soft stone. It resists copper. It resists most simple hand tools. And yet somewhere between the pounding marks at Aswan and the drilled cores from Giza sits a question that has never fully closed. What were the ancient Egyptians actually using to cut it? If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The textbook answer has held for more than a century, and it holds for a reason. Ancient Egypt did not have iron tools in the Old Kingdom. What they had was copper, a soft metal that bends before it bites into hard stone, and dolerite, a dark volcanic rock harder than granite itself. The accepted account says workers shaped granite the slow way, by pounding it. They took fist-sized balls of dolerite, raised them, and brought them down again and again against the same patch of stone, grinding it into dust one blow at a time. Multiply that by thousands of workers and thousands of days, and a granite obelisk becomes possible without a single metal blade touching the hardest part of the job. It is not a glamorous answer. It is not meant to be. It is meant to be sufficient, and for a long time it was treated as the end of the conversation. The trouble is that sufficiency and completeness are not the same thing. Pounding explains how a block gets its rough shape. It explains the shallow trenches at Aswan, worn smooth by repetition. What it struggles to explain sits somewhere else entirely, in a smaller and far less famous set of objects that most visitors to Egypt never see, because they are not standing in a quarry under the sun, they are sitting in drawers. The Unfinished Obelisk earns its place at the center of this story because it is the rarest kind of archaeological find, a project caught in the act. Most ancient granite work that survives is finished, polished, and moved into position centuries before anyone alive today could examine the process that made it. This obelisk was meant to stand nearly 42 meters tall and weigh more than 1,000 tons, which would have made it the largest single piece of stone Egypt ever attempted to raise. It never got that chance. A flaw running through the granite widened as the workers cut beneath it, and rather than risk the entire block, they stopped. The stone stayed attached to the bedrock on 3 sides, half-freed, and it has stayed that way ever since. Walking along its length today, you can see the trenches the workers dug around it, each one lined with the same rounded, overlapping depressions, evidence of the pounding method at its most direct and least disputed. This is the wall the standard account is built on, and it is a real wall. The marks are exactly what repeated blunt force against granite should look like, and there is no reason to doubt that this is largely how the rough separation of the stone from the ground was carried out. Where the story gets more complicated is in what the pounding method does not touch. Shaping a rough block is one kind of problem. Boring a narrow, straight, perfectly round hole through solid granite is a different one, and it is here that the accepted explanation starts to strain. In 1881, the archaeologist Flinders Petrie was cataloging material recovered from sites around Giza when he described a small group of stone cores, cylindrical plugs of granite and diorite that had clearly been removed from the center of a drilled hole, the way the core of an apple is removed by a corer. What caught his attention was not that the holes existed. Drilled holes in ancient Egyptian stone vessels and sarcophagi were already known. What caught his attention was the pattern left behind on the cores themselves. A tight, even, continuous spiral groove running around the cylinder from top to bottom, as regular as thread on a screw. A groove like that does not come from pounding. Pounding leaves a scatter of overlapping dents, not a clean helix. A spiral groove of that consistency comes from something turning, cutting into the stone as it rotates, the way a drill bit cuts into wood. The accepted theory, developed and tested in modern experiments, holds that Egyptian workers used a hollow copper tube, pressed down and rotated by hand or by a simple bow mechanism, with wet sand poured into the gap as an abrasive. The sand, not the copper, would have done the actual cutting, since quartz sand is harder than both copper and, in places, the granite itself. Turn the tube long enough, feed it enough abrasive, and eventually it bores a clean cylindrical hole, leaving a core behind exactly where Petrie found one. Tested slowly, patiently, by hand, this method works. Modern experimental archaeologists have replicated it and produced holes that look convincingly similar to the ancient examples. That is the honest and important part of this story, and it deserves to be said plainly before anything else. Nobody needs to invoke lost technology to explain that a copper tube and an abrasive could bore a hole into granite. The theory is sound, and it is where the wall stands its firmest. It is worth sitting with the scale of what the theory is being asked to explain before moving past it. The Serapeum at Saqqara holds more than 20 granite boxes, each one weighing somewhere between 60 and 80 tons, hollowed out from the inside with walls of near uniform thickness and corners cut close to a right angle. The granite sarcophagus inside Khafre's pyramid shows interior surfaces flat enough that a straight edge laid across them barely rocks. None of these objects are mysteries in the sense of having no explanation at all. Every one of them can, in principle, be accounted for by patient hand labor, copper tools, and abrasive sand, given enough time and enough workers. What they share is a level of internal consistency that becomes harder to explain the larger and more repeated the object gets. A single drilled hole with an irregular groove would be unremarkable. Dozens of large hollowed boxes, cut across what were likely different work crews and different reigns, all converging on a similar standard of flatness and symmetry, is the detail that keeps researchers returning to these sites instead of filing them away as solved. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The crack in that wall is not the method itself, it is the math. Several engineers who have examined the surviving cores closely, most prominently Christopher Dunn, an engineer who has spent decades studying ancient stoneworking, have pointed to something that the tube and sand explanation does not fully account for. The pitch of the spiral groove on some of the cores, meaning the distance the groove advances with each full rotation of the drill, is remarkably uniform along the entire length of the cylinder. In hand-powered rotary drilling with loose sand abrasive, the cutting rate depends on constant, even pressure and a steady, continuous rotational speed, both of which are extremely difficult for a human arm to sustain, without variation over the time it would take to bore through several inches of solid granite. Dunn's argument is not that hand-powered drilling is impossible. Experiments prove that it isn't. His argument is that the specific consistency measured on certain cores implies a mechanical stability that freehand rotation struggles to reproduce, something closer to a fixed, weighted, continuously driven apparatus than a person leaning on a bow drill and refilling sand by hand. This remains a genuinely disputed claim. Most Egyptologists maintain that variation in ancient hand tool marks is within normal range for skilled, practiced labor repeated over a working lifetime, and that no mechanical explanation is required. The debate has never been resolved in either direction, and both sides are arguing from the same handful of physical objects sitting in the same museum drawers. Dunn's published measurements describe the spiral advance on one particular core sample as holding to a pitch tight enough that, scaled up across the full depth of the drilled hole, a hand operator would have needed to maintain an almost unchanging download force and rotational speed for the entire duration of the cut, without the natural slowing, correcting, and re-gripping that occurs whenever a human body performs repetitive work over an extended stretch of time. Critics of this reading point out that only a small number of cores have ever been measured this closely, that a single, unusually consistent example does not establish a rule, and that skilled repetitive labor can, in practice, achieve far steadier results than casual assumptions about human fatigue might suggest. Both objections are fair, Both remain unresolved because the underlying sample size is so small that a handful of additional measured cores could shift the argument meaningfully in either direction, and nobody has yet undertaken that fuller survey. This is the seam where the channel has to be honest about what is documented and what is theory. It is documented that ancient Egyptians used copper tools and abrasive sand on hard stone. It is documented that the resulting cores show tightly spaced spiral grooves. It is genuinely disputed, among people who have physically examined this evidence, whether unaided human hands could have produced that specific consistency, or whether something else, some device built to hold a drilling tool steady and turning at a fixed rate, stood between the worker and the stone. Nobody credible on either side of that argument is suggesting the work was done by anyone other than Egyptians. The debate has never been about whether ancient Egyptian engineers were capable of extraordinary things. The debate is only about which specific tool sat in their hands while they did it. That question becomes harder to dismiss once you look at how the Egyptians themselves chose to record their own craftsmen. Old Kingdom tomb walls are covered with scenes of daily work, preserved because Egyptians believed depicting an activity in this life helped guarantee it in the next. Among the carpentry, the metalworking, and the farming scenes are craftsmen shown drilling stone vessels, bent over their work with tools whose exact mechanism artists rendered in outline rather than technical detail. Hieroglyphic inscriptions accompanying scenes like these use specific determinative signs, small pictorial markers attached to a word to indicate its category, for the tools of stoneworking. Some of these signs depict simple hand implements. Others are drawn with a form that does not cleanly match any single surviving hand tool, closer to a weighted, cross-armed shape than a chisel or a mallet. Egyptologists studying these determinatives are honest about the limits of the evidence. A stylized sign carved by an artist working from convention, not from a technical drawing, cannot be read as a blueprint. It cannot tell us the internal mechanism of a machine, if a machine is even what it depicts. What it can tell us is that Old Kingdom Egyptians distinguished, at least in their own writing, between the tools used for ordinary carpentry and something else, a category of implement specific enough to earn its own sign, used specifically in contexts involving hard stone. That distinction matters more than it might first appear. A civilization does not usually invent a separate written symbol for a tool, unless that tool is genuinely separate in function from the ones already in use. The chisel had its sign. The adze had its sign. Whatever the craftsmen bent over those stone vessels were using earned a sign of its own, distinct enough that scribes reached for a different mark rather than reusing an existing one. Reliefs from workshop scenes add another layer to this without resolving it. Several surviving Old Kingdom images show two figures working together at a single stone vessel, one crouched low near the base and the other positioned above, hands raised at chest height in a posture that has been read, depending on the researcher, as either steadying a drill shaft or working a separate crossbar mechanism connected to it. Egyptologists who favor the cautious reading point out that Old Kingdom artists frequently compressed or simplified physical tools for the sake of a clear composition, and that reading a precise mechanical device into a stylized pose risks seeing more than the artist intended to show. Researchers on the other side of the argument counter that the pose recurs across multiple tombs from different periods with enough consistency that it looks less like artistic shorthand and more like an attempt to depict something specific, a two-person operation involving a fixed vertical element and a separate applied force, exactly the kind of division of labor a weighted drilling frame would require. Neither side can settle the question from the images alone, because a two-dimensional relief was never meant to function as an engineering diagram, and every attempt to read one that way runs into the same limitation. None of this proves the existence of a lost machine, in the sense that phrase usually implies. There is no surviving diagram. There is no intact device sitting in a museum waiting to be identified. What exists is a chain of real, physical evidence that does not fit together as cleanly as either side of the debate would like. Real trenches at Aswan showing patient, direct, unglamorous hand-pounding. Real drilled cores at a museum in London showing a level of rotational consistency that some qualified people believe exceeds what hand power alone reliably produces. Real hieroglyphic determinatives distinguishing hard stone tools from ordinary ones. in a way that suggests the Egyptians themselves considered this category of work to require something specialized. The theory this channel is built to explore, stated plainly rather than dressed up as settled fact, is this. Somewhere in the workshops attached to Old Kingdom quarries, Egyptian engineers may have built more than a hand tool. They may have built an apparatus, a weighted or geared frame, designed to hold a copper tube steady, feed it abrasive at a controlled rate, and turn it with a consistency no single pair of arms could guarantee across the length of a long cut. Not a power source beyond human labor, and not a technology imported from anywhere else. A machine in the oldest and most literal sense of the word, a mechanical advantage built by human hands to do what human hands alone could not do reliably. If that reading holds, it does not diminish the achievement of the pyramid builders. It expands it, because it means the people who raised the unfinished obelisk were not only skilled laborers repeating a slow, brutal task for decades, they were engineers, solving a precision problem the same way engineers still solve precision problems today, by building a tool to remove the variability a human hand cannot remove on its own. What the theory cannot yet do is name the device. No drawing survives detailed enough to reconstruct one. No workshop has ever been excavated with the remains of a mechanism still in place, a wooden or copper frame that could have held a drill tube under constant pressure and turned it at a fixed rate. The determinative signs remain stylized rather than technical. The core samples themselves, 6 of them at the Petrie Museum and a handful more scattered across other collections, have never been subjected to a full, independently repeated physical analysis broad enough to settle the pitch consistency question once and for all. Every measurement cited on either side of this debate comes from a small, finite set of objects, most of them examined decades apart by researchers working from different assumptions about what they were looking for. That is where the unfinished obelisk earns its place in this story one final time. It is still there, in the ground at Aswan, uncut and unmoved, because the ancient project that made it was interrupted before it finished. In a strange way, so is ours. The tube and sand method is proven capable of drilling granite. The consistency of certain surviving cores remains, for now, only partly explained by it. Somewhere between those two honest facts sits the actual answer, and it has been sitting there for 3,500 years, waiting for someone to look closely enough at 6 small cylinders of stone to finally close the case. A full modern survey would not be difficult to carry out. High-resolution laser scanning could measure the pitch of every surviving core to a fraction of a millimeter, across the entire set rather than the handful that have been examined by hand and eye over the past century. No museum has yet committed to that project. The cores sit catalogued, protected, occasionally displayed, and largely unexamined at the level of precision the question actually requires. Until that survey happens, both sides of the debate are working from partial evidence, and both know it. The cautious explanation may turn out to be completely correct once the full data set exists. The engineered apparatus theory may collapse the moment someone measures enough cores to show that the tight spiral pitch was never as unusual as a handful of examples made it look. Either outcome is possible, and either one would still leave the ancient Egyptians exactly where they belong, as the people who solved this problem themselves, using tools built by their own hands for a purpose their own writing thought important enough to name. Until then, the granite keeps its secret, and the spiral groove keeps turning, in a stone drawer in London, toward a question nobody has fully answered yet. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.